All right, guys. This is the first video in the physics course. I'll be making a lot of them. And this one is about measurement, uncertainty, and significant figures. This will cover the content that's on page 48 through 51 of your Essential Physics textbook. I mention that because some guys like to read, other guys like to watch videos and listen, so I'm leaving it up to you guys which one you prefer. But I will say that these videos do emphasize what I think is important. They are essentially my lecture notes. So at least watch the video, and if you need some more content, some more practice problems, some more explanation possibly, you can go back to your Essential Physics book and look in there. Also, make sure you check Canvas. As you're taking these notes, there's some questions and key points listed on the assignment on Canvas that you guys should make sure that you include within your notes as you're taking them. All right, so having said that, let's get going. So when we talk about measurement in science, as I mentioned in class, we measure things, and that's how we get our information about the world around us and the universe. And then based on these measurements, we can analyze it, and that's how we come up with our laws and theories. That's how we test our hypotheses. But the thing is with any measurement is when we have a group of measurements, we're kind of interested in two things, and we want to maximize both of them. The first one is accuracy, and I know you guys have, probably heard this in your science course before, but I want to make sure everyone knows it. Accuracy is how close a measurement is to some true value. So when we're talking about accuracy, there's some accepted or there's some known value that we can compared our measurements, and if our measurements align with that value, if they're close to it, then we say they're accurate. If they don't, then it's an inaccurate measurement. So an example would be if we're using a scale or a balance and we want to measure the mass of something. We have these calibrated masses with the accepted value, say it's 500 grams, right? If we put this on the balance and the balance reads 500 grams, then we know, or at least close to it, then we know that it's an accurate measurement. However, if the scale doesn't, then we know it's miscalibrated in some way, shape, or form. This can happen with scales. It can happen with meter sticks. If you notice the meter sticks in class, especially on the end, some of them, they're kind of like rubbed off on one end. And so if you start measuring from the very end, it's not going to be very accurate because, essentially some of the meter stick is actually missing. So watch out for that, guys. Anyway, when something is inaccurate, it leads to error. Okay, so error isn't something that necessarily you mess up. Error can result from an instrument that's miscalibrated. It's not set up correctly. Okay. Now the other thing that we think of with measurements is this idea of precision, and so there's the idea how close are these measurements to each other? How closely are they gathered? And so very often we use this dartboard to illustrate the two, right? So precision, roughly speaking, the more decimal places you have, the higher the precision of your measurement. And so that's when we worry about sig figs, which we'll get to in just a sec. When we take our measurement, we want to make sure that we accurately record the precision to whoever wants to use that measurement, who's ever looking at that measurement, which is why it's important to record it with the proper number of sig figs and estimate that last digit. So when we talk about precision, whereas error measures accuracy. If we have low error, it means that's a pretty accurate instrument. With precision, we measure something called deviation. And deviation is, how much things differ from each other. So the higher the deviation is, and we can calculate this, but the higher this deviation is, the lower the precision is going to be. Okay, so if things differ a lot from each other, then we would have a high deviation but low precision. However, if they're close together, we can have very high precision, and we would have a low deviation. So those things are kind of inversely related to each other. Okay, so I want you guys to know these terms. I want you to know the difference between them. And I know it's hard, especially with our common everyday speech, but try to be disciplined on how you use error and how you use deviation, how you use accuracy, and how you use precision. Especially accuracy and precision, we tend to use those two words interchangeably, and it can lead to some confusion. All right, so uncertainty and measurement. Here's the deal, guys. Every measurement has some uncertainty. So this is the thermometer that I showed you guys in class, and this idea that this is a Celsius scale, and I could read to essentially the tenth of a degree Celsius, which is pretty good. But I have to estimate what that tenth is, and there's some uncertainty there. Now, this doesn't mean that's a wrong measurement. It doesn't mean it's bad. It doesn't mean that we don't have any knowledge. But realize that uncertainty isn't every measurement, and that is not a source of error. I'm going to be asking you guys in lab to record sources of error. A source of error is not having to estimate a digit, okay, or having to read it by eye instead of having it be digital. There's always uncertainty. It's understood, and it's not a source of error. Okay, so just be aware of that. There's other causes of uncertainty as well. It could be that you are measuring it wrong. Okay, that would be a source of error. But just having to estimate that last digit, yes, there's uncertainty there, but that's not error. Okay. All right, so as you said, we have these measurements, and especially with precision, we want to communicate them accurately. And so when we have a measurement, we have a certain number of what are called significant figures. Okay, significant figures, there's this idea that these figures are important, right? And they are important because they communicate our measurements to other people. Now, this has more of an effect when we start doing calculations with our measurements, but one of the first steps in getting there is just realizing how many significant figures a number has. So shown here are the rules that we use for sig figs. And you guys can read the screen. I'm not going to go through. I'm not going to read this word for word. But if there's any non-zero number, that's going to be significant. That's not a problem. Zeros are a little bit trickier, so I'll give you some examples here. These what are called leading zeros. So these zeros right here, they're just they kind of show you where the 2, 9, and 6 go. So those are not significant. And then at the end of the numbers, sometimes they're significant, sometimes they're not. It depends on whether there's a decimal there or not. Okay, and then numbers between sig figs are significant. So let's practice this just a little bit, and you guys, feel free to pause the video and try to make guesses here, and just predict, okay, how many sig figs are in each of these measurements. So we have 450 meters. There's no decimal here, and the zero's at the end of the number, so this is not significant, but the 4 and 5 are, they're non-zero digits. So this one would have 2 sig figs. Okay, so 2 sig figs right there for that. The 4 and the 5. Then there's this one. Okay, 0.0.01040. I put a bunch of zeros in here for you guys. Let's see if I can trip you up. So, like I said, feel free to pause the video and make a guess if you guys want to. These zeros are leading zeros. They're not significant. They just tell you where all these other numbers go. This zero is in between two non-zero numbers, which are significant, so therefore this one's significant. This zero is at the end of a number, but it's also after a decimal. So again, look for this decimal. Okay, a zero at the end of the number and after a decimal, both have to be true, is significant. So in this one, the 1, the 0, the 4, the 0 would all be significant, and this would have 4 sig figs. Okay, and then finally, we have this one. How many would this one have? Well, we have the 962 for sure. We have a decimal, a 0 between two non-zero numbers, then a 0 at the end. And so looking at all this, we have a 0 at the end and after a decimal. And so we would have 6 sig figs here. Now this will become, as I said, much more important when we start doing calculations. And if all we did was take measurements, it'd be kind of boring. The real power in measurements and in science is when we can take those measurements and we could do calculations or make graphs with them. But in order to do that correctly, we have to know how many sig figs, because there's rules. If we do a calculation using measurements, then our results, our answer, will also have to have a certain number of sig figs. And we'll get to that later on in class. So again, all measurements have uncertainty in them. We can categorize measurements by accuracy, how accurate they are and how precise they are. Accuracy having to do with how close to accepted value, precision, how many decimals there are and how close together they're packed. There's this, and then we talked about sig figs and how we can find how many sig figs are a number. So I hope this all made sense to you. If not, please ask me questions in class, and we will practice this next class and see how you guys do.